Okay, let's dive right into this explainer. Today, we're uncovering the core architecture that makes Linux literally the most ubiquitous operating system on the planet. We're going to break down how a system built entirely from scratch by a single student evolved into the highly complex, massively scaled powerhouse running everything from your local servers to global cloud computing networks.
To really appreciate the sheer scale of what we're about to explore, we got to start with a pretty surprising hook. Back in 1991, in a humble Usenet post, Linus Torvalds announced he was building a free operating system. And he famously added that it was just a hobby and won't be big and professional. Well, that contrasts beautifully with the immense, highly professional powerhouse it is today. What started as a fun side project built on a 386 PC with just 4 megabytes of RAM has fundamentally transformed the technological world.
So here's our micro to macro roadmap for this explainer. We're going to build our foundational understanding layer by layer. First, we'll look at the monolithic kernel foundation. Second, organizing the Linux file system. Third, the system boot sequence. Fourth, scaling to the cloud. And finally, mastering complex kernel configurations.
All right, let's jump into Section 1, the monolithic kernel foundation.
Before it was even a fully realized operating system, Linus Torvalds was actually experimenting with Intel assembly language on his PC just to learn about multitasking. He wrote this simple program with 2 tasks. One thread would write a continuous stream of the letter A to the screen, and the other would write the letter B. You could physically see the context switches when the stream of A's suddenly became B's. It sounds incredibly simple now, but this tiny, rapid handoff of CPU resources, that was the very first iteration of what would eventually evolve into the Linux kernel. It proved that a single processor could be managed to juggle multiple tasks seamlessly.
So, the crucial thing to understand here is how this foundational layer actually operates today. Linux uses what we call a monolithic kernel architecture. And what that means is the entire kernel, managing literally everything from your CPU scheduling to memory, device drivers, and file management, it all operates centrally within a privileged area called kernel space. Because everything runs in this single, unified space, the components can talk to each other instantly, with almost zero overhead. It makes the system incredibly fast and super responsive to hardware changes, providing a highly stable platform for all the user applications running above it.
Moving right along to Section 2, organizing the Linux file system.
Now that we have our core, we need to understand how Linux logically organizes data. And a truly elegant feature of Linux is its realistic tree structure, which is governed by the file system hierarchy standard. Notice how absolutely everything radiates out from one single point, the root directory, which is represented by just a simple /. So, unlike other operating systems that might use different drive letters for different physical disks, Linux seamlessly mounts every single file, directory, and device somewhere under this one unified tree, creating a completely cohesive environment regardless of the underlying hardware.
Let's briefly step through a few of these key directories, just to demystify how system resources are logically separated from user data. First up, the /bin directory. This holds your essential command binaries, basically the everyday tools you use for listing or copying files. Then there's /boot, which contains the critical files needed to actually start the system, including the kernel itself. /etc is your central hub for system-wide configuration files, keeping all those settings logically grouped away from the software executables. And finally, /var. This is designated for variable data, meaning files whose content is constantly changing while you use the system, like error logs or temporary email spools.
Okay, so we've organized the data. Now we need to secure it. And this brilliantly illustrates the elegant logic of Linux security. Every file and directory is governed by a really strict yet simple set of permissions that cleanly divides access into 3 distinct categories: the user, who owns the file, the group assigned to the file, and, well, other, which is everyone else.
The whole mechanism breaks down into a tangible string of just 9 characters. You have R for read, W for write, and X for execute. So if you see an RWX, that means full access. And this exact string repeats 3 times in a row, once for the user, once for the group, and once for others. Think of it like this. If a script is marked with an X for your user, you can run it. If it isn't, the system blocks you right out. It's that simple. This straightforward grid provides total foundational security for every single file on the system, ensuring that applications and users only access exactly what they are explicitly permitted to.
All right, Section 3, the system boot sequence.
With our file system structured and secure, let's look at how a Linux system actually wakes up. The boot process is basically a sequence of really precise handoffs. Step 1 is hardware initialization, where your BIOS or UEFI checks the basic hardware, finds the boot device, reads the first tiny sector, and then essentially passes the baton. Step 2 is the bootloader, typically something called Grub2. Grub2's specific job is to load our monolithic kernel straight into memory. And once that kernel is up and running and the hardware is managed, it hands control over to Step 3, the init system. This is the very first user space process that wakes up absolutely everything else.
It is so fascinating to trace the evolution of this init system. Traditionally, Linux used something called sysvinit, which basically just executed a sequential series of startup scripts based on predefined run levels. But as systems grew more and more complex, this sequential, one-by-one process became a huge bottleneck on modern multi-core processors. So today, Linux heavily utilizes systemd. This modern init system acts as a comprehensive manager that analyzes dependencies and actually starts unrelated services in parallel. This drastically speeds up boot times and brings the entire system up to specific targets, like a graphical interface or a multi-user command line environment.
Moving on to Section 4, Scaling to the Cloud.
Let's step up to the macro level now. The massive global success of cloud computing is actually built on a Linux kernel feature called namespaces. Think of namespaces kind of like isolated rooms in a giant house. You can put a process in a namespace and it gets its own completely private view of the system, its own process IDs, its own networking stack, and its own mount points. It literally thinks it is the only application running on the whole machine. This brilliant separation forms the absolute core foundation of modern container technology, keeping thousands of cloud applications from interfering with one another on the exact same physical server.
But, isolation isn't enough on its own. You also need resource management. If namespaces are the separate rooms in our house analogy, then cgroups, or control groups, are the rules that dictate exactly how much electricity and water each room is allowed to use. Cgroups limit and track the resource usage, like CPU time, memory, and disk I/O, for these isolated groups of processes. When you combine them with namespaces, cgroups ensure perfectly fair resource allocation and completely prevent one runaway application from hogging all the server's resources.
And finally, Section 5, Mastering Complex Kernel Configurations.
Now, this number right here, it's honestly mind-blowing. The modern Linux kernel contains over 15,000 interdependent configuration options. 15,000! That creates a combinatorial explosion of possible ways to compile the operating system. Navigating this is just no longer a task a human can easily do manually, especially when you're trying to optimize the kernel for really highly specific hardware use cases. Because of this sheer vast complexity, software engineers and researchers literally require machine learning today just to tame the kernel. Practitioners use ML for performance prediction, estimating what the kernel's binary size or execution time will be before they even waste time compiling it. They use feature selection to isolate the tiny core subset of those 15,000 options that actually matter for their specific goal. And they use ML optimization algorithms to hunt down the exact configuration that will minimize resource usage without breaking the whole system.
So, why is this so absolutely crucial? Well, it enables what researchers call performance specialization. By mastering these thousands of interdependent toggles, developers can hit extremely specific performance thresholds. For example, they can use ML to pinpoint the exact configuration needed to compile a minimal kernel that is strictly between 20 and 50 megabytes in size. Having this granular logical control is exactly what allows Linux to be perfectly tailored for highly constrained hardware, like a tiny Internet of Things sensor that has virtually no memory to spare.
And here is where it all comes together. The exact same monolithic kernel architecture that can be stripped down to just a few megabytes for a tiny IoT device can also be configured to run massive, high-performance computing data centers. By managing hardware centrally, organizing data beautifully, booting efficiently, and using namespaces to isolate cloud containers, Linux scales seamlessly across the entire spectrum of computing.
Which brings us to our concluding thought. We've traced the architecture from Linus Torvalds toggling A's and B's on a 386 PC, all the way up to complex machine learning models managing 15,000 kernel configuration options for the cloud. How did a hobby system built in a 1991 dorm room logically scale to power everything from Mars rovers to the modern internet? It scaled because of the beautiful, collaborative, and fiercely capable architecture of open-source computing. The only remaining question is, what will this community build on top of this foundation next? Thanks for learning with me today.